Probably don't have, I'm not quite as entertaining as Bill is, but in some sense to give you a flavor of some of the spatial effects and timing effects, and I think I'll pick up on the idea that Bill talked about, the global nature of this event. This is really a big earthquake, and we're going to bring it back home at the end because this is exactly the kind of event we'd expect in the Pacific Northwest. So, and many of you have probably heard this story over the last month. But so one of the questions as we think about the impact of this event on the Japanese, what is the impact going to be to us when it happens here? And in 1700 it did. And as we look forward, it will again. The other thing is, the other take-home message to me about this is time. And this wonderful thing about time and geologic processes. And the fact that the energy that we saw released in that earthquake and the actual faulting went on for about 200 seconds. That energy had been stored over several hundred years. So we've been putting money into the bank, we've been putting strain energy into the crust for several hundred years, and then released all that energy over the course of a couple hundred seconds. And the impact on the cultures. On the other hand, the recurrence rate of these earthquakes is much greater than your or my lifetime. So how do we as humans think about how we prepare, how we invest, and what we do? And Yuri showed us how the backpacks in preparation. I'm not sure that's going to happen in Seattle or Portland when the event in the Pacific Northwest occurs. So I think those are some of the kind of really interesting things that we can take home from this event. Now, usually people stop me because they can't understand what I'm talking about. So as I'm talking, please, if you have a question, just ask the question, and we'll move through in some sense. So I'm going to start this talk. Now, I didn't do the talk this morning, but when I got up this morning, I downloaded this image, and this is a starting point for us. This is, you can see we're sunrise here in Texas. And everything in red are earthquakes that have happened in the last 24 hours. Everything that's in yellow are the earthquakes that have happened in the last 2 weeks. And everything that's purple are the earthquakes that have happened over the last 5 years. And so I think this captures the fact that we live on a dynamic Earth. And that you can see the seismicity even today, a month after the event, is dominated by this earthquake that's occurred. And we've seen these 2 magnitude 7 aftershocks. And we'll talk a little bit about the size of the events as we move forward. And so it is a global problem, and it is a global issue. And hopefully we'll have some understanding, particularly about this part of the Earth and what's going on here in some sense. But I'm going to go back in time to 1855. And earthquakes occur in cycles. 1855, there was a relatively large earthquake near Tokyo. Several thousand people lost their lives, and it stimulated interest in understanding earthquakes. And maybe, I don't know, maybe when we're done today, that understanding, well, you will think that our understanding is no better than this. But these are a set of block prints. I always wish I had one of those. That began to be published after this earthquake. And the idea was earthquakes were caused by catfish. It's kind of a neat model. And that these catfish, very large catfish, lived in underground pools. And Namazu, they were the catfish, and they were controlled by the deity, or Kashimi. And the stone was the way that he was able to control the earthquakes and keep them under control. When this event occurred in 1855, as I understood it, it was a deity holiday, so they were out of Tokyo at the time, and so the catfish became rambunctious. Now it's interesting, the story, this particular block print, the story is that apparently this catfish is complaining that the reason, and I have no clue why this is, but the reason that he was rambunctious, or she was rambunctious, was because the Japanese were turning away from catfish for their diet. They wanted more catfish to be in the diet. That doesn't seem to be useful for the catfish's life. But that was the argument. Now, hopefully we know a little more today. So I want to go and talk about the quantitative nature of this event. How big is it? How long was the fault? How long did it last? Where did it occur? And it goes back to making measurements. And so when earthquakes occur, they're going to generate waves through the earth, and we've learned this over the years. And so we have a global network of seismographic stations. This is the network that's operated by the United States Geological Survey, the National Science Foundation, and a consortium of universities, of which SMU is a member, called IRIS. And these are the stations that went into the assessment of this event, the real-time warning, and the data that went into the tsunami response along the way. It's an interesting side story. This network came about in 1960 as a result of the U.S. government's desire to monitor nuclear explosions around the world. And so the first part of this network was installed, and it's a Dallas story, that a manufacturer here in Dallas manufactured these instruments and deployed them around the world. Some of you may know Jack Hamilton, who's recently passed away. Was a member of the Devon College board. Jack was the one that manufactured and put these instruments around the world. And for some reason in 1960, the data set was open to everyone and distributed freely. And it set the stage for free exchange of data ever since that time period. So what do we do with the data? So I'm going to go to 2 days before the main event. So we're on the 9th of March. And Tokyo sits down here, so we're offshore, and a small event occurred. A magnitude 7 event occurred on that day. And when that event occurs, these seismic waves are going to travel around the globe, and they're going to travel really fast. They travel kilometers per second, so that when an earthquake happens in Japan, the first arrivals are here within minutes in Dallas. And so that provides the ability to very quickly read those, take those readings, and then locate the event. Locate the event within minutes of it happening in the case, and when we get to the big event, it's actually located while the event's still going on. And so this provides the ability to say something about the event. And so these colors down here mean something. Red means bad, green means not so bad, in terms of the amount of ground motion. And so immediately this kind of information comes forward, and you can see that everything's green here, probably was well felt, but this wasn't a terrible event, and we're going to come back to that. And then this is something called Pager that any of us can sign up for. Again, it characterizes the amount of ground shaking, but it estimates the fatalities and economic loss within 10 to 30 minutes after the event. And this is used for emergency response. Now this magnitude 7, you can see they're all over here in terms of the green. But this was a precursor from this fault system where energy had begun to be stored on the 9th. And then it's followed on the 11th, the event that Bill talked about, magnitude 9. Magnitude unit is logarithmic, so this is a factor of 100 bigger in ground motion. It's actually a factor of 1,000 bigger in energy than the previous. We've zoomed out a little bit, so we're here. Here's Bill in Tokyo. This is now the fault that broke that morning. It's magnitude 9. So to put this into perspective, it's about 450, 500 kilometers long in this direction, so 350 miles, 400 miles, and a couple hundred kilometers across. It's a big piece of property that moves. We're going to find out it moves by 40 meters. So I don't know how big this room is, but 120 feet of motion along that. It's a big material. Now you can see the colors are oranges and some reds. Immediately we see that when you look at some of these, violent ground shaking, heavy damage. So within about 30 minutes of the event, these are the warnings that are given to the government officials because of the ability to record these events. Now we go over here to this pager, and you can't, I apologize for the graphics, but 30 minutes after the event, these two bars say that there have been between 1,000 and 10,000 people who have lost their lives. It's an amazing number and And they also, and this is based on population density, where it occurred, they make an immediate estimate of the dollar economic. So somewhere between 15 and 30 minutes, the estimate's at $100 billion. Whereas we see today it's 350. This does not include the tsunami. So, but it kind of provides you an idea, an insight into these kinds of efforts along the way. So the question is, why did this event occur? And I think probably everyone in here understands plate tectonics, but I thought I should say something about this in that this box right here is what we were looking at before. And so we've got the mainland of Japan, and we have the Pacific Ocean out here, which was the center of my picture that we started out with. This very thin oceanic plate that's moving in this direction relative to the mainland of Japan. It's moving at about 8 centimeters a year, so a little faster than my fingernails grow. And that energy, as it's moving, the boundary between, and this is the oceanic plate, and there's the continent, that boundary remains locked. So I'm pushing 8 centimeters a year, year after year, and you can think of it as a rubber band. I'm storing energy in that rubber band over a course of several hundred years. So if you take 8 centimeters, multiply by a couple hundred years, suddenly you get to numbers like 10, 20, 30 meters of stored energy that when that fault breaks, that energy that's stored in 200 years is released in 100 seconds, and you see the effects that we talked about. And so this is an important characteristic. What we're going to come back and see is that these kinds of events, we call these super thrust events, account for, in the course of 4 or 5 earthquakes, account for most all the energy released on the surface of the Earth in the last 100 years. And so they don't happen every day, fortunately, but it's that storage process that gives us an idea. Now we've zoomed into that purple box, and this is the first of the images that, what we're going to see is 37 years of earthquakes, so that's 1974. This is the region that we're going to see is going to break. But over the last 37 years, there have been hundreds of events, but these are all very, very small. But they provide some insight into where the fault is, what the strains are that are accumulating on the fault system. We can see little pockets of events. These are small events and aftershocks on the order of magnitude 7s. This is some of the subduction zone on the back side of the events. But it's very clear that this is a very active event, but there's not a lot of big events that are occurring in this region, and so it's relatively, there's relative strain accumulation along this part. And so it was an area that we would expect earthquakes to occur. Come back to the idea about time history. If we look back over the last 800 years, this part, and it's going to be this part of the fault that's going to break, or that did break on the 11th, has typically had magnitude 8 earthquakes over the last 800 years, not magnitude 9. So many magnitude 8s. What we're going to see is the event that occurred on the 11th is actually 5 events, 5 subsections of the fault that break, that when they're added together do the magnitude 9. The importance of that is, why indeed didn't that nuclear reactor, why wasn't it designed to withstand this particular earthquake? Well, the earthquake design for this was magnitude 8, not magnitude 9, because of that historical data set. If we do go back, though, about 800 or 900 years ago, there is apparently a magnitude 9 event at that time period. And what we're going to see is sometimes the fault breaks in little pieces, sometimes it all breaks at once. It's a philosophy in engineering design for buildings, whether or not we do a probabilistic or deterministic model for, and in this case, this was a deterministic model, which is based on recent earthquakes in that region. A probabilistic model takes into account what might happen, and so a probabilistic model would have had designs for magnitude 9s rather than magnitude 8s, and I think we've all watched what the impact of that is on the power plant and the tsunami. I'm going to go on because I think And so, as a result, this magnitude 9 earthquake, and I'm not going to show these. But to bring it back to home, and this is Bill's thing, that these are global events, politically, economic, aid-wise, but they're also local events in terms of these seismic waves that we observe. And so this is probably more than you want to know about some of these things, but one of the most exciting things for me as a seismologist right now is something called EarthScope. And it's kind of an Earth telescope that's moving across the United States. It's a National Science Foundation project, and it has 400 seismometers. There's every 72 kilometers, and over the 15 years they're going to move across the United States and then across Alaska to provide us a telescope to look into the Earth. And fortunately, right now they're around us right here in Dallas. And so this is the location of this telescope right now, and we're looking and beginning to look at the structure of the central part of the United States. We're moving towards New Madrid and the Mississippi embayment. 100 years ago this year, there was a series of 3 magnitude, high magnitude 7, 8 earthquakes. Would have caused damage here in Dallas, not great damage. Certainly would have had tremendous impact on cities like Memphis and St. Louis, although there weren't very many people at that time. And so these telescopes not only look into the geology, but they provide us an opportunity to look at some of these kinds of events. And so these seismometers are employed, they're deployed underground, they have telemetry, they've got a cell phone, and they can deliver data in real time. And as a result, they recorded this event in Japan. So we're sitting here in Dallas. We're going to look at this record right here. Is in Nebraska. I don't know why they didn't include one in Texas, but this over here is 0 is when the earthquake happened, and this is 10 minutes, 30 minutes, 2.5 hours after the event. And what you're going to see is at about 15 minutes, you're going to see the waves from the event in Japan sweep across Texas. And we actually sit, this is the Earth, we sit about 80 degrees from Japan. So you're first going to see the events that go the short way, and then you're going to see the events that go the long way and come back the other direction. And so you're going to see these waves sweep across from the your upper left down, and then you're going to see them come back and these are the records. Now the interesting thing to me is this little bar is about 1 centimeter. So what we see here is here in Texas, we have about an inch. The ground motion moves up and down multiple times by about an inch. That's remarkable to me, that an earthquake all the way around the world. Now, on the other hand, the period of these are very long, so we don't feel them very well. Oh, let's see. Here's the P wave, and you can you see the reds and blues as they move across. That's the vertical motion, and then the tails are going to give us the horizontal motion. So those are the S waves that are moving. You can see them sweep across. Gives you an idea how the wavelength of these waves from peak to trough, they are very long. And then these giant surface waves that come across. And then we begin time of quiescence. With these P waves, by the time we get into here, the event has already been located. That pager event has gone out. They've estimated how many people have lost their lives, and the emergency response is going. But the Earth continues to move, and now we can begin to see the waves that have come the other direction around the world. So they've gone the long ways and come back around. These waves allow us to characterize the event. They allow us to characterize the subsurface. But in some sense, they bring it home, at least to me, that even though I'm a long ways from this event, I'm connected to it. And in some sense, because of Uri and all, we have some responsibility in this process. All right, I'd like to talk just briefly then about the tsunami that is the other part of this process. If we think of this as the Pacific plate that's moving underneath the Japan, this is backwards from, but what we'll see here is, and I'll give you a flavor of what's going to happen. Same thing, for a couple hundred years, This is moving down, but this is connected, so it's going to strain this piece, and then and we're going to generate the resulting tsunami as it begins to move out. This wave travels about a factor of 30 slower. It travels about the same